So we are very happy to be the 13 of us together today to listen to Fleur Gaudfernau, who just defended her PhD thesis basically in late December. That was done under the supervision of Stéphanie Lassonnière and Erwan Le Pennec. And so that now I'm very happy that you're going to present it and basically work as a postdoc in our team for a few months. And then I don't know what you will do.
So hello everyone, thank you for inviting me. I'm going to present basically half of my PhD thesis work. So this is more about the methodological side, which was about multiscale optimization for shape registration. So first of all, I'm going to present the motivation behind my thesis. So the idea is that we started from very clinical questions, and more specifically, we were interested in fetal brain MRI, which is a very peculiar kind of data. So the idea is that in hospitals, clinicians acquire raw fetal brain MRI, and from these images, after several pre-processing steps, you can acquire different types of data, such as brain volumes, segmentation images, and cortical surface meshes. Researchers use this data to perform quantitative analysis of the fetal brain, for example, volumetric analysis, analysis of the cortical folding process during pregnancy, and finally, building spatio-temporal atlases, which are reference images or objects of the fetal brain during pregnancy. And so to summarize, the goal of my thesis was to introduce a new kind of analysis in this domain. And our goal was to use deformation-based analysis to perform the quantitative analysis of the fetal brain. And this means that we wanted to apply deformation models to fetal brains. So to properly understand what we wanted to do, I'm going, sorry, this is, okay, that's better. I'm going to introduce computational anatomy. This is based on the idea of describing differences between shapes through deformation of the ambient space, and this will allow us to perform the statistical analysis of shapes. So briefly, we typically have a manifold which constitutes a group of transformations, and in this manifold we can compute distances between deformations. And the idea is that we will use the distance between deformations to compute distances between shapes, and typically we will consider the distances between two shapes to be the length of the shortest path between these two shapes according to a metric. And so in this thesis, to analyze fetal brain MRI, we have used two main models of interest. First of all, cross-sectional models, which can also be called the deformable template models. So the idea is that from cross-sectional data, we are going to estimate two things. One, a representative image of our data set, and the anatomical variability around this mean image, which is represented by the deformations going from this image to each of our subjects. And secondly, we used temporal models, which we used to model the evolution of a phenomenon with time. So to give you a brief idea of the main applications in computational anatomy, so we can use cross-sectional models to estimate representative shapes in a population. We can also perform analysis of the anatomical viability of a population by by applying statistical tools such as PCA on the template to subject transformations. We can also use registration tools to perform some kind of transfer of information. For example, to segment a brain using an already segmented template brain. And finally, we can use temporal models to model organ evolution with time. As I said, the goal of my thesis was to apply deformation models to fetal brains. And so to do this, we had to answer several key questions that range from more methodological questions to questions that are more about clinical applications. And so in this presentation, I am mainly going to speak about the first key question, which was the methodological one about how can we estimate realistic anatomical deformations. And then we also add, as I said, more clinical questions, but I will not go into this kind of details today. So I will present in this talk our multiscale strategies for estimating realistic object deformations. So first of all, I am going to give you a bit of a mathematical background. So in my thesis, we always computed shape transformations using the LGDMM framework, which is a convenient framework for for computing shape transformations. So the idea is that we have, so the problem is represented here in its most simple form. And the idea is that we have a source object that we want to map to a target object by computing an unknown transformation between these two objects. And so in the LGDMM framework, the deformations that we are trying to estimate is called phi, and it is a diffeomorphic deformation, which is topology preserving, which is very convenient, very important in a clinical framework. And so in the LGDMM, we are constructing our diffeomorphism by integrating time-dependent velocity fields according to this flow equation. And so the idea is that to compute the transformation between our source object and our target object, we are going to integrate this equation between time 0 and time 1. And so here you have the source object at time 0 along with the time-dependent velocity field. And you can see the time-dependent velocity field that deforms our object with time. And so at time 1, we obtain a deformed source object that is hopefully close to the target object. So in this setting, what we want is actually phi of 1, which is our transformation at time 1. But instead of optimizing phi of 1, we will optimize the velocity fields that define phi of 1. So to do this, first of all, as in most computational anatomy problems, we will try to minimize a cost function, which is typically composed of a data attachment term and a spatial regularity term. And so here we are specifically interested in the spatial regularization term. So we are trying to estimate velocity fields which are very high dimensional, and our problem has possibly an infinity of solutions. And so we need to restrict the dimension of the problem and the number of solutions. And so to do this, we use a finite parameterization of the velocity fields. Basically, we say that our velocity fields, which are represented with red arrows, are defined as the linear combination of momentum vectors that are located at control points. And this parameterization depends on a regularizing kernel, which defines a RKHS. And so this definition is really important because this means that from now on, our vector fields belong to a RKHS, and that we actually can define our vector fields by estimating the momentum vectors, which are the blue arrows, alpha of t. So this is a very convenient assumption. This now means that instead of estimating directly the very high dimensional v of t, we now have a finite number of parameters. We can also use the norm of the RKHS to estimate a metric on the control points. And so this means that the possible solutions to our problem will be geodesic path with respect to this norm. And finally, a very convenient property of geodesic path is that they are fully determined by the initial conditions of the problem, which are, in our case, alpha of 0 and c of 0. So to summarize, how do we compute shape transformations in this specific setting? We can use a very efficient gradient descent algorithm. And so to compute transformation between shapes, we actually need to know only the initial momentum vectors and the initial control points. So from the initial momentum vectors, we can perform geodesic shooting and compute the value of the momentum vectors at any time t. Then, by using the RKHS kernel that I introduced, we can infer the value of the velocity fields at any time. Finally, by integrating the flow equation, we can compute our diffeomorphism phi of t. And finally, we can apply it to our source object to obtain the deformation of our object with time. And so now to get into the subject, why is multiscale optimization needed? And it's actually really important to understand that the structural assumption that you can see here is very convenient, but also very restrictive. And so one very important consequence is that the size of the RKHS kernel will actually determine the spacing between the control points and thus the momentum vectors. And these control points are set on a grid. And so here, this is illustrated. So typically, the user chooses the size of the RKHS kernel, which is in this case a Gaussian kernel. So if you choose a small kernel, this means a small spacing between control points and thus a high number of parameters to estimate. And if we choose a large kernel, this means a smaller number of control points and a lower number of parameters to estimate. And this is actually a very important constraint in this setting. And this leads to a typical dilemma. So on the left, you can see that if you choose a small kernel, you have to estimate an elevated number of control points. And as the problem is highly non-convex, we have an elevated probability of estimating a very inaccurate deformation. On the contrary, if we use a large kernel, we will have a stronger regularization of our velocity fields, and we will estimate smooth deformations, which will also be very inaccurate. And basically, we can summarize this by saying that deformations are constrained to a single scale, which is the size of our kernel. And this is, of course, a very inaccurate assumption, especially when we are analyzing clinical data. So the solution that we are proposing here is, first of all, to introduce multiscale optimization that preserves the LDDMM kernel. So the idea is that we still want to preserve our original structural assumption, And so we keep our original definition of the velocity fields as the interpolation of momentum vectors located at control points. And we will actually add another regularization layer by using the HeKA wavelet transform. And we will use the wavelet functions to implement a coarse-to-fine optimization, meaning that we will impose additional smoothness constraints during optimization on the velocity fields, and we will progressively relax these constraints in order to incorporate finer and finer scale coefficients to our velocity fields. So to get into more details, I'm going to briefly present the HeKA wavelet function. So this is the simplest wavelet basis, which is used to perform the multiscale decomposition of signals. And it relies on a collection of nested spaces. So on the left of the screen, you have the spaces of local approximation. And these spaces can basically be used to compute local means of functions. So here, this is illustrated, of course, in one dimension. And on the right, we have the spaces of local details, which can be used to approximate the details of function at several scales. And of course, you recall that in our setting, the function that we want to transform is actually defined on a grid, since our momentum vectors live in a 2D or 3D grid. And so here I am going to explain how we adapted the HeKA wavelet transform to functions that are defined on a grid. So here you have the classical decomposition of any grid function. So our function f is a two-dimensional grid function that you can typically decompose as the sum of unit basis function. And we can consider that this decomposition is based on approximation coefficients that we consider to be at scale 0, meaning the smallest possible scale. Now I want to go from this classical decomposition to the wavelet decomposition. And for this, we are going to use the forward wavelet transform, which allow us to write another decomposition of f in different bases. This is based, first of all, of a decomposition based on approximation coefficients, which will summarize the low frequencies of our grid functions. And then we can add the detailed coefficients to our approximation. So here, the detailed coefficients summarize higher frequencies of the signal. And finally, we can add other detailed coefficients which are defined at the highest frequencies of our signal. And so this is just to illustrate that if we apply this kind of wavelet decomposition to our momentum vectors, we can actually easily separate between low frequency and high frequency components. And we can simply decide to silence some of the detailed coefficients. And if we silence such detailed coefficients, we will actually estimate momentum vectors that are smoother than the original momentum vectors. And so this is exactly what we did to improve our algorithm. And so our algorithm is based mainly on the forward and inverse wavelet transform, which allow us to switch between two different bases.
And Fleur, because I think that many people here, and especially many people today, are not super familiar with the wavelet transform. So can you maybe explain, like, what exactly do you mean with the wavelet decomposition? Like, like for instance, this 4x4 square that you are decomposing, is it so it's in pixel space, right? It's not in wavelet space.
it's in the space of the momentum vectors.
Yes. Okay.
So, but it could be in pixel
Okay.
space. It's basically the same.
So just to be clear, basically this decomposition, it's exactly like each coefficient corresponds to a wavelet coefficient.
Yes. So actually, I think this one is simpler to understand. The idea is that the wavelet decomposition that you can estimate from a one-dimensional function, you can just transpose this kind of decomposition very kind of easily to grid functions. And the idea is that it works very simply by computing local averages at different scales. So what we call scale is that typically at the finer scales we will compute very local means, and when we go to higher scales we will compute less local means of the signal. And when we compute the average values of a signal, obviously we lose some of the detailed coefficients, and these detailed coefficients are stored in another kind of space. I'm not sure it's much clearer, sorry, but the idea is that we can actually decompose our function into average coefficients and detailed coefficients to really decompose what constitutes the mean values and the local differences of our signal at different scales.
And so, for instance, so if you come back to the other slide, because you say, okay, so here basically we can recognize in the lower half of the slide like the difference HeKA wavelet in 2D, and you say, okay, maybe we want to keep just the low frequency ones, but if you just wanted to do that, why wouldn't you just use a Fourier transform and keep the low frequency modes?
Could we localize?
Because it's less, because yes, wave is also localized in space, not just in frequency.
Yeah.
That's the difference.
It was done already in the LDDMM framework, but this was used to reduce the computational cost, because yes, the idea is not the same if we just use the Fourier basis to smooth to erase the high frequency components. We have no idea where they were located, so it's just a way of smoothing the signal, but you can't actually perform cost-to-fine optimization.
Okay. So that's because in practice you're going to be adaptive, so you're going to keep some high frequencies, for instance, in regions of the brain where it's going to deform heavily.
We did this, but not in this presentation. It's not mandatory actually, because the algorithm is already adapting himself, so we don't really need to be locally selective. But we have a version of the algorithm where we actually are locally selective. So is it good? Or
I have a very small question. I don't know just what you said. How do we decide how to make it locally selective or not?
I think I will speak about this later.
Okay.
But it basically depends on the amount of signal on the image, because I don't know if that's very clear, but actually this part is really the most important part, and it's the idea that you will deform objects by using a grid of momentum vectors, and these have coordinates on their a momentum vector as a coordinate on the grid of the momentum vectors, but you also know where the momentum vectors lives on the image that you are trying to deform. And so you can just identify empty areas of an image and decide that you want to have smoother vector fields in these areas.
So it's going to be put beforehand, or just
that's during optimization, because the idea in cost to find strategies is that we always start by estimating the smoother possible vector fields, and so we can really decide step by step which components we incorporate, but actually the simplest solution is the best one, and it is better to just incorporate all frequency, whole detailed coefficients progressively into the signal, regardless their localization on the grid. And so if you don't have any more questions, I'm just going to get into the main algorithm, and so we go one step above, and I hope this will be a bit more clear. And so the idea is that here what you see is actually a single iteration of the original algorithm. And as usual, it iterates between two simple steps. Step 1, we compute the gradients, and step 2, we perform the update of the parameters. To get into a bit more details, when I say, so we are still trying to estimate velocity fields. And so here in blue, you can see the initial momentum vectors that are the parameters that we are trying to estimate. And so I will not get into the detail of how we compute the gradients of these momentum vectors, but our original algorithm is just the repetition of these two steps, computing the gradients of the momentum vectors and updating the momentum vectors. And so the idea in our multiscale version is that we are only going to modify the second step of our algorithm. So we will preserve the gradient computation step and only modify the second step. And so the idea is that our original algorithm was actually defined in the RKHS basis that I already presented. And the idea is that now we are going to perform some operations in the wavelet basis by using the forward wavelet transform. So first of all, we introduce the coefficient beta of 0, which are simply the wavelet coefficients that corresponds to the initial momentum vectors. And so this is these coefficients are actually equivalent to the momentum vectors in the sense that our momentum vectors can be seen as coefficients in a RKHS basis, and the wavelet coefficients can be as coefficients in a wavelet basis, but the two representations are of course equivalent, and you can go from one to the other. And so the idea here is that we are going to use this other basis, and we will also use the forward wavelet transform to obtain a wavelet representation of the gradient of the momentum vectors, which is once again strictly equivalent to the representation in the RKHS basis. And then, since we have the wavelet representation of the momentum vectors and their gradients in the wavelet basis, we can simply perform the same parameter update step, but in the wavelet basis. And if we use the inverse wavelet transform to go back to the original RKHS basis, we actually obtain our updated momentum vectors. And what you see here is actually strictly equivalent to the original algorithm, to the difference that we have used another basis. However, we want to perform multiscale optimization, and so to do this, we will just add a tiny step to our optimization, which means that right after the parameter update step, we will perform some kind of fine-scale silencing step, which means that depending on the current scale that we are at, we will just set to 0 some of the finer scale coefficients of the updated wavelet coefficients of the momentum vectors. And now, if we go back to the HeKA spaces, we actually obtain updated momentum vectors, which are smoother than in the previous version. And so this is one iteration of the cost-to-fine algorithm, and every iteration is basically proceeds in the same manner. The only difference is that since this is a cost-to-fine algorithm, when we are at the coarser steps, we are going to silence more fine-scale coefficients, and when we are at the finer scales, we are going to silence less and less fine-scale coefficients.
In practice, you perform a full optimization at one scale and then go to the final one.
Yeah.
So like a second floor.
Yeah, it's truly step by step. And in the end, when we reach the finest possible scale, we stop silencing our fine scale coefficients, and we actually go back to the original algorithm, in the sense that we don't need to use the wavelet basis anymore. And so in theory, we could achieve the same results as the original algorithm, but as we will see in the following, this is not the case, and this is what you see here is actually just an optimization trick to trap the algorithm in more optimal deformations. So in this work, I developed several multiscale strategies. So briefly, we have the multiscale momenta strategy, which is the one that I just introduced. So this is based on a wavelet filter that we applied to the vector fields to estimate finer and finer velocity fields during optimization. And so we coupled this algorithm to a multiscale objects algorithm, which is based on multiscale representation of our objects. So when our objects are images, we just used a Gaussian filter, and when our objects are meshes, we used a Laplacian filter. And so this means that we have actually 4 different algorithms: the original algorithm, the multiscale momenta algorithm, the multiscale objects algorithm, and the dual multiscale algorithm, which combines the 2 multiscale algorithms. So first of all, I am going to present a simple registration example to show you how the multiscale algorithm operates on multiscale momenta algorithm operates on a simple example. So on the left, you have a source image that we want to register to a target image using a HeKA kernel of size 4. And so we have compared how the original algorithm works compared to the multiscale momenta algorithm. So here we go. And so in the middle, you can see the transformed source image. So here we are at the coarser scale and at the second coarser scale, sorry. And so you can see that the original algorithm estimates from the very beginning velocity fields that are composed of quite high frequencies. Whereas the multiscale momenta algorithm is, for the moment, only composed of smooth vector fields. And so here we go down one scale and we progressively incorporate finer and finer scale coefficients. And now we are at the last scale and there are no constraints anymore on the momentum vectors. And so, as you can see here, we basically reach two similar results and two similar velocity fields to the difference that the multiscale momenta algorithm estimates velocity fields that are more regular. And so at this step of the presentation, we can ask ourselves what is the interest of the multiscale momenta algorithm since we actually managed to achieve very similar results. And I will now introduce more complicated experiments to show you in what manner this kind of algorithm can be of use.
I didn't get why the scales appear why you start with course and then you said, okay, I had some. So
yeah, it's I didn't I did not find any clearer way of explaining it. So here the lines that you see are actually a representation of the current scale. So this means that when we are at the maximum scale, the momentum vectors that are inside the same square will actually be forced to share similar equal values. And this is what you can see here. Oh, it's okay. It went too far, sorry. This is what you can see here.
But it means that you're at time zero, you get only the square, which is
yes.
And then you add in time so at time zero you just have the course of scales, time one you have the full scales, and you add scales. But it's a choice, how you add scales. Yeah, it's okay. It's not during the
it's during the optimization. I think it's already the optimization of initial momenta.
Yeah, but you flow everything at you flow everything.
Yes.
You flow every scale between 0 and 1.
No, for one scale, you do sorry.
So here, so what you see here is just the full optimization process. So actually here, this is the estimated flow.
Okay. So we are during the gradient descent.
Yes.
Yes.
Okay.
Yes. And so to go down one scale, we actually just wait until the algorithm is close to convergence, and then we go down a scale each time we are close to convergence. And here it's actually quite easy to see that the scale that we are at is sufficient, and that we are reaching convergence. And so here we go down one scale, which means that our momentum vectors are forced to move together by groups of 4. And so this is what you can see here. Oh, okay. And here we are reaching the finer scale, the finest scale, which means that we don't have any more constraints on the velocity fields. And yes, this process is only during optimization, and this is not when we don't use the wavelet representation when computing the flow between the two images. This is a different setting.
So you are doing successive optimization, like you are doing at one scale, get the flow, then refine the flow with another scale. So I mean, like do you the whole optimization process for one scale, then you from the deformation you do another optimization.
This is the same optimization. We actually run iterations of the optimization at one given scale until we are close to convergence, and then we just release some of the constraints on the momentum vectors to add our finer scale coefficients, but this is still the same optimization process.
Okay.
It just means that at one given iteration, instead of stopping the algorithm, because when we are close to convergence, we just want to stop optimization. We actually add, we allow the addition of some details into the velocity fields. This is actually very typical in coarse-to-fine optimization, where you just optimize a transformation at a coarse scale. When you're close to convergence, you add finer and finer scales. So this is just really an optimization trick, and it's just the idea is that by doing this, we know that we push the algorithm towards better solutions in practice.
Okay, so you use a coarse scale to reach some point of optimization while you add a finer scale.
Yeah.
Okay. Okay, so
yeah, because the idea is that when you are at the coarser scales, of course there are less possible solutions. And if you just use a very smooth vector fields to register two images, you will actually have less probability of falling into unrealistic local minima. And so by doing this is really a way of, at each step, pushing the algorithm towards a more realistic local towards more realistic local minima, even if we have no theoretical guarantees in practice. This is how this works. Because as you can see in the original algorithm, since we have less structural constraints on the velocity fields, we can actually the algorithm can very easily decide to just split the image and almost create holes, even if in theory this is not possible with diffeomorphisms. We can very easily fall into unrealistic local minima. And so the idea is that we are trying to avoid this using this strategy.
And maybe the thing is that everyone in shape analysis does at least a two-step registration, where first you fit a rigid transform, and then you do your registration. And here it's about adding intermediate layers. So it's I think it behaves very similarly to if we were doing annealing on the kernel size, on the size of the deformation kernel.
On the choice of the sigma, it's better to have a small sigma, because when you use high frequency, when you use low frequency, it's how you choose sigma like that.
Yeah. So this is really the choice of sigma is really the main issue, because even when implementing this kind of algorithm, the results are still strongly dependent on sigma. And if we use a large sigma, the benefits of coarse-to-fine optimization are very less present. Because why do coarse-to-fine? This would be coarse to less coarse. I guess this wouldn't be very interesting. This is I have no real solution to this problem. This is really a no ways present problem, and even when using coarse-to-fine optimization, if we use a very small kernel, we can still have issues, because when you use a really small kernel, you will tend to really avoid smooth or large transformations, And so if in this very simple example, if we choose to use a kernel which is of size 1 pixel, actually the algorithm will just decide to favor a really small scale transformation, even if we use the cost-to-find algorithm. If the end scale is a very small scale, it will always favor these transformations that exist at this scale. And so this is really, I think, a problem that is really linked to the framework that we use in itself.
That's great. But what are the differences in behavior with the LDDKM, another one where we use multiple signature kernel?
Yeah, so I have a slide about this actually, I think. No, it was in appendix. It's okay. And so the idea is that so this is this part of the slide, and when we use mixtures of kernels, so we are still dependent on the size of the kernels. And the idea is that the user has to choose a number of kernels that we will just overimpose. And so I guess I should begin with a more general idea. And in the LDDMM framework, there are two main ways of performing cost-to-find optimization. So the first one is the one that you talked about, the kernel bundle framework, which is about coexisting flows. And this is not really a cost-to-find optimization. This is more coarse and fine optimization. And when you read the papers, it is actually a kind of, it's not very convenient, I think, because when doing this, we actually lose the RKHS structure because we are trying to overimpose several different RKHS. And so just without getting into the details, the optimization is going to be much more complicated. And actually, if you read the last papers, I think they used deep learning to estimate their coexisting flows. So I think it's a nice framework, but not in practice, since it would be quite complicated to use. And the idea is also that you are still very strongly dependent on the different scales, and I'm not sure that the result would be as optimal as when we perform cost-to-find optimization. And then there are another kind of solution which was based on composing flows. And these are less known papers, and they are more theoretical, I think. And it resembles more what we are doing in the sense that it's still, we go from coarse kernels to finer and finer kernels. But we still need to choose the kernels, and once again, the mathematical model is very complex, and so this complicates the way the optimization is performed. And I guess what differentiates our solution is that the mathematical model at core is the same as in the original algorithm, meaning that we are still using a single LDDMM kernel, and we can still compute the gradients in the same manner as before, which is very, and so we just use the original algorithm to compute shape transformations, to the difference that we just choose an optimization trick to silence some of the higher frequency.
It's related to projected gradient descent. Like it's an operator that projects your gradient in terms of space. Like you shut up some frequencies, you make some steps, and then change the projection operator by adding some frequencies.
I'm not sure what you're asking.
Like you are not using the standard gradient, you make a complicated stuff like going to some wavelet spaces, you kill some
Yes.
frequencies, and then you change the direction, you project your gradient onto some
Yes.
space, you go make some steps.
Yeah, so we modify our gradients, but the idea is that we don't change the way the gradients are computed. And so this is really the main difference between our algorithm and these solutions. Ours can really be used in different settings, even with large dimensional images. And actually, the only additional complexity of our algorithm stems from the use of the wavelet transform. But since we did not modify the computation of the gradients, we have almost no additional complexity.
Yeah. I mean, it's for me, it's cheaper than defining many scales, like you add K10, K5, K1 stuff, so which is could be expensive. So the good idea, like I think the weighted transfer is almost free, like and log n, or maybe there is fast stuff to do that.
Yeah.
So it could be interesting, but still you get stuck on the choice of the
Yes.
of the bandwidth, initial bandwidths to get something reasonable. Maybe you can penalize the high frequency also, avoid the effect you described.
Yes.
Like going to the finer scale, because obviously you have better operational term.
And another solution that I read about, I think it was about ear shape registration. It was the idea was really, I think, the most intuitive idea. They performed registration using a large kernel. Then, when the optimization ended, they took the result and iterated the optimization process, but using a smaller kernel. And so this is really the cost to find idea in the most basic sense. The difference is that it's really costly.
Yeah, but here again, you stay in the same space. You just modify the gradient. You just project the gradient. You just modify the direction design, but you stay in the same pages.
Yeah, so I think the solution I was talking about is maybe not very elegant, but it's convenient and practical.
I did that. I truly did that.
For the kernel bundle, I thought that in the end it amounts to just summing the kernels.
Mm-hmm.
So it's quite easy to test. Like it's because apparently you said that it was complicated, but I think there is a theoretical interpretation where you have like coexisting flows. So the mathematical analysis is quite complex, but I think they proved that in the end you just make a sum of kernels, so it's very easy to test.
Yeah, the sum of kernel, I agree. It's a simple solution, and it's more simple than other types of solution that use the modules, for example. But I think that I do not come from optimization, and the idea in the beginning of my PhD was that we were using a software called HeKA, where the LDTM framework and the optimization algorithm, which I introduced, they were implemented in HeKA, and the idea was that we were lazy and we wanted to be efficient because we had very high dimensional objects. And so the idea was that we were not going to modify the computation of the gradients. And if you sum kernels, you lose this. So I don't think that I have the formula of the norm, but actually when we use this formula, we can easily compute the norm of the vector fields and use this as a regularity term. And if we have a sum of kernel, we are not in a single RKHS anymore. So
Yes, we are. We just the kernel is the sum of the kernel.
Yeah.
So it's a kernel and it's a
Ça,
haircut.
c'est une pénalité d'hypothèse, ça peut être une pénalité déformétrique. Le coup de diffuse déformétrique.
but I think there was I think it was more. I don't know much about computing the gradients, but I think when computing the gradients from the new cost function, it was more complicated. No?
So I don't know about the from triple, but we do it all the time in our applications. It's really the same algorithm. We'll replace the Gaussian kernel with the sum.
Okay, so you just modify the cost function and derive those things.
So I mean, maybe you could try actually, because with your model, it's multiscale, but maybe you could use a multiscale kernel also, like a sum of
We
kernels.
can.
It could be interesting.
Yeah, the thing is, the sum of kernel works only when we are Gaussian, because what they say in the paper is that in general, if any kernel, like if with any kernel, it's not working, you can add it and you have like a different kind of different momentum, different direction that you cannot sum up. And when you use a sum of Gaussian, kind of it's working, and there you can sum up all of this, and then you have the same, and it's quite easy to implement.
Let's maybe discussion. Because in your case, you use Gaussian. Or...
Yeah.
Gaussian.
And what was it the cost of the wavelet transform? Like it's just
It's linear.
it's linear. Yeah, so it's like even in 3D.
Not really. And we also tried in the very beginning. We tried another solution with which wasn't a good idea. It was a kernel with a varying size depending on its location, and that's when we realized that we were losing the RKHS structure, and that we needed to be careful about keeping this part. And so this is why I think we are more our algorithm is more about an optimization trick that really a change of the mathematical model at core, since we still have the very same definition of our velocity fields. And this is also why it's convenient, because we could try to apply this trick to other mathematical frameworks. So now I will present some of our experiments. So to show you how the multiscale algorithm can reach more optimal results. So first, we worked on atlas estimation, which are already introduced. So the idea is that we have a set of objects from a cross-sectional data set, and we want to estimate a representative object from the population, which represents the mean, and we also want to estimate template to subject deformations, which represent the variability. And as usual, we try to optimize a cost function, which is composed of data attachment terms and regularity terms. And so in this example, we used the L2 norm to compute the distance between images. So to evaluate our algorithm, of course, we divided the evaluation procedure in two steps. So we used cross validation procedure, in which we performed in the first step atlas estimation of the training set, and in a second step we used the average template estimated during atlas estimation to register our template to each image in the test set. And so in the results that I am going to present, we evaluated our algorithms by computing the residual error. which is basically the L2 norm between the deformed template and each of our images. So if we take a look at some of the quantitative results, on the left you can see the performance during atlas estimation, so the training step. And we performed our cross-validation procedures using different kernel sizes, meaning different numbers of control points. So you recall that the higher the number of control points, the smaller the kernel is in size. And so we compared the 4 algorithms that I presented, the original algorithm, the multiscale momenta, multiscale objects, and dual multiscale algorithm. And so here you can see that our original algorithm has pretty low performances, especially when using small kernels, which was to be expected. And we can see that the 3 multiscale algorithms are able to reach higher performances. And we can see in particular that the dual multiscale algorithm is able to achieve the best performance. So now we are going to see what this means in practice.
Sorry, what is the error? Error is what?
Sorry?
What is the residual error?
It's the L2 norm.
L2 norm,
Yeah.
sorry. Okay.
So this is actually what we optimize.
Okay.
And we also, so I don't have, I didn't present the results here, but we also computed the similarity index metric to perform evaluation with a metric that was not in the cost function, and we basically obtained the same results. And so, yeah, sorry, I forgot to say that so in this example, we performed atlas estimation on hand-drawn toy data that you can see here, which are just characters, which gives us results that are quite simple to interpret. So in terms of the qualitative results, now we can see the template images that have been estimated using a quite small kernel, which corresponds to 100 of control points. And so here we can easily see that the original algorithm estimates template images which have many erroneous features, which is not the case for all the multiscale algorithms. And now if we look at some of the reconstructed training images, which means the template image deformed by the template to subject transformation, we can still see that, of course, for the original algorithm, we have still very false reconstructed images. And we can actually see that we have some inaccuracies that are yielded by the multiscale momenta and multiscale objects algorithm. So this is what you can see in red circles, and so this can be used to understand why the dual multiscale algorithm has a bit of a higher performance compared to the 2 other versions. And so we concluded that it's important to combine the multiscale momenta and the multiscale objects strategies. So now we also applied our multiscale strategies to another computational anatomy model. So we studied 2 models, the well-known geodesic regression model, which is similar to the idea of linear regression, but applied to shapes. The idea is that we have observations that are defined at a given time, and we want to estimate 2 things. One, a representative object, and 2, the mean geodesic trajectory that deforms this object. And we also studied piecewise geodesic regression, which was developed by Juliette Chevalier. And so the idea is that it's very close to geodesic regression, to the difference that our average trajectory is actually decomposed into p different geodesic trajectories. And this is actually very convenient in a clinical setting because this allows us to introduce changes in trajectory dynamics. And so we wanted to see if our optimization algorithm could in fact improve the optimization of such models. So in terms of evaluation, so we designed another evaluation procedure. The first step consisted on atlas estimation on a subset of the training set and geodesic regression on the training set. And finally, during test, we performed registration on the test set, meaning that for each test subject, we extracted the template of the same age from geodesic regression and perform registration between the age matched template and our subject. And so, as usual, we used the same evaluation metric as before, which is the residual error. So first of all, I'm going to present our simplest results, which are on the on toy data, which are very similar as before. So here we were trying to model the trajectory of a character, which is quite a complicated trajectory, which is composed of a jump and a landing from a character. And so in terms of quantitative results, so these times we did not compare the three different versions of the multiscale algorithm. And here, when I speak about multiscale algorithm, I am actually referring to the dual multiscale algorithm. So since we showed that it's the best version of among the multiscale algorithms, we were not interested anymore in comparing the different versions. And so here we actually compared the original versus the multiscale algorithm. And we compared geodesic regression versus piecewise geodesic regression, in this case, the 5-component geodesic regression. And so here, very quickly, we can see that during training and test, the best performing algorithm is the multiscale algorithm associated to the 5-component piecewise geodesic regression, which was to be expected since, of course, a 5-component trajectory is going to perform better than a 1-component trajectory. But interestingly, we can see that our multiscale algorithm still achieves better performance than the original algorithm. So in terms of qualitative results, so here, using a kernel of size 10, you can see the 1-component trajectories, examples of 1-component trajectories that are estimated by the original and multiscale algorithm. And very simply, you can see that these trajectories are not very accurate, which was to be expected because the trajectories that we are trying to model is too complicated to be modeled by a single diffeomorphism. Now, if we look at the 5-component trajectories, we can see that, in fact, the original algorithm still estimates trajectories that are inaccurate, which is not the case of the multiscale algorithm, which manages to achieve quite accurate trajectories. So now, if we take a smaller kernel, we have very similar results. We still have very erroneous trajectories estimated when we use the 1-component regression. And in contrast, if we use the 5-component regression, we see that the multiscale algorithm is still capable of estimating quite accurate trajectories, which is a very encouraging result. And so since my PhD was about clinical applications and specifically modeling the changes of the fetal brain during pregnancy, we now applied our multiscale algorithm to the modeling of the fetal brain intensity changes during pregnancy. And so for this, we used fetal brain MRIs from the Fetal data set, and we wanted to model the volumetric changes of the fetal brain between 22 and 35 weeks of pregnancy. And so here you have just some examples of the results that we obtained, and we can see that very interestingly, the original algorithm is unable to estimate very accurate trajectory. And if you're familiar with brain MRIs, you can see that it actually estimates anatomical features which make no sense, especially at the boundary between the boundary of the cortical gray matter. And this is not the case when you look at the multiscale algorithm, which is able to estimate much more accurate fetal brains. However, if you look at if you look at the state-of-the-art atlas, which is presented on the lowest panel, you can see that even if we are managing to achieve a quite good trajectory, this is not an accurate enough trajectory, and this is one of the main issues in my PhD, because since diffeomorphism or topology preserving, it is actually very difficult to accurately represent brain changes that are actually very complex during pregnancy. And so we can conclude from this part of the presentation that when we apply such algorithms to clinical images, our multiscale algorithm can help avoid some typical pitfalls, but it cannot, of course, repair some of the flaws that are inherent to the LDDMM framework. So we also took an interest into modeling the development of the cortical surface during pregnancy. And this was actually a more adequate task because the LDDMM framework has less difficulties modeling the changes of cortical surface meshes compared to modeling intensity changes. And so the task was the same as before. We wanted to model the evolution of the cortical surface of the fetal brain between 22 and 35 weeks. So once again, here we have some examples that compare trajectories that are estimated by the original versus the multiscale algorithm. So in this case, we are using a 4-component geodesic trajectory. And we can easily see that our multiscale algorithm avoids falling into unrealistic local minima. So this is what you can see here in red circles. We can see that the original algorithm tends to deform in a very inaccurate manner some areas of the brain, which is not the case of the multiscale algorithm. So here you can see another example of unrealistic local minima, which was estimated by the original algorithm. And what is interesting is also the fact that this is not reflected by the residual error. You can actually see that there are very few, the difference is quite small between the error of the two algorithms, which means that using just computing the distance between the objects that we are trying to move closer is not a good metric to properly evaluate our algorithm. Yes.
You use varifolds there?
Yes. Yes. So I didn't have time to to be precise, but yes, this is the varifold distance.
And do you use multiscale varifolds or?
No. We had a version where we used where we were smoothing the varifold representation, but actually it was more efficient to directly smooth the meshes when performing multiscale optimization. But these are really two options for performing the multiscale optimization on objects.
And here, do you do remeshing of your?
No.
You don't have like triangles that become too large that cannot fold?
No, actually, this was an issue in the beginning, but since when performing geodesic regression, I actually give an initial image to an initial object that has to be deformed, and I just typically gave the algorithm a sphere with a high number of triangles, just to avoid the problem of having to deform a mesh composed of too few triangles.
Okay. Because you have an hyper template formulation.
No, it's not a hyper template. It's just the initial. In this kind of algorithm, we always need to give an initial object, even if it's just a sphere or.
You didn't try to register two data from the same subject. I'm not sure you can have this, but at the time, the first one to the second one, only the trajectory that you estimate.
Yes.
From your ideal template.
Yes, so the idea is that I know that usually geodesic regression is used on data extracted from the same subject, but in our case, it's actually very difficult to obtain longitudinal data from fetal subjects, and so the idea is that we are simply trying to estimate the mean trajectory from our data set.
Thank you.
How high is the resolution of the mesh?
Sorry?
How high is the high resolution mesh?
It was 200,000 triangles. I tried going higher, but it was too costly. But it does affect the results because if we go lower, as Barbara said, we have very terrible faults. And so to conclude with this presentation, here I presented several multiscale strategies whose goal is to foster realistic object transformations. So these strategies are efficient in the sense that they provide high quality templates and deformations and have an ability to generalize to unseen data. They are also practical in the sense that they add almost no additional computational cost, and they are versatile in the sense that they are compatible with several models and different types of objects. So as I said, there still is a strong limitation of choosing the deformation kernel. And finally, we had very interesting perspectives in terms of applications, and these were about the clinical applications, which I just got to talk about very briefly, because you can have an algorithm which is efficient on our during experiments and on our test data. But the goal of this thesis was also developing algorithms which were very efficient and could really meet the demands of clinicians. And so this is what I will not present, but just to give you an idea, this multiscale algorithm is currently being used to estimate a spatial temporal atlas of the fetal brain during pregnancy. And so we and there is also the very important question of implementing open source tools. And we will be working with Jean and Louis to hopefully manage to provide convenient and open source multiscale algorithms.
Just on this last sentence, in what are you implementing the multiscale? In which language?
Python.
Python. Okay. Yes.
It's a fork of deformetrica, or it's just another?
Sorry?
It's a fork of deformetrica, or another? So it's still the trunk is
No, because deformetrica was developed in Aramis, and I don't think they have anyone working on deformetrica anymore. So everyone has his own branch of deformetrica, and we need at some point to publish a common version.
Good luck.
Yes, no. So basically, what we decided to do, that's why Louis was hired through Stéphanie's money, and so that's what the Psychic Shapes project is about. So I don't know if in 3 weeks or maybe in 6 weeks, we can show you the first working demo, like it was yesterday or the day before yesterday, that I obtained from Stéphanie, that it will be published under a very permissive MIT license.
Okay.
She didn't.
No, because at first, because she was vice president of valorization, she's kind of team, let's do strange licenses. But no, okay. Like we agreed, okay, we're going to make it very permissive. And so I think that's definitely the idea. Louis has been working a lot on multiscale decompositions of meshes, etc. And I think that now that we have this foundation, it's going to be easy to implement basically those strategies. I think on meshes, for instance, you wouldn't, I think, bother with a volumetric wavelet decomposition, but basically you can keep those ideas and put them into a good pipeline, because it's come down to annealing and working first at the core scale and then at the lower scale. I think that's how those things are going to be packaged.
And so how is it ready, or how will it be easy to take it? How long?
You mean
If I want to try to use a multiscale algorithm, should I code it myself from scratch, or?
Yes, for now, I think so. We'll provide some basic implementation, like maybe the one without any multiscaling, etc. And at the beginning, we are providing tools separately, and maybe you can integrate on them. We are just providing some basic tools, have clear implementation, and after that, I think you need to write your own script to everything together. But maybe in the future, in the next month, we will integrate use in the library, like multiscale strategy. So we have some kind of multiscale. Yes. So basically, most of the components are there, but for instance, it's time intensive to keep the Docker up to date for kiops, etc. So it's all a question of prioritizing things. I think it's realistic to say that basically when Fleur leaves the team, it's done. So that's basically in 6 months. 6 weeks. I think it's 6 months. It's very realistic.
You're in postdoc.
Yeah, so I'm doing a postdoc in the same team, just so we finish.
Last forever.
Okay.
And the optimization that you use, it's gradient descent or LDJS?
It's a gradient descent. They implemented LBGS, but I'm not sure. I don't think it's working currently.
Okay.
So, yeah.
It's an adaptive.
Yeah, we have adaptive step size, and we also had to adapt the adaptive step size because when you perform the cost to find step, especially on objects, when you defilter an object, you need to change the step size because typically we need this makes the gradients become very high in terms of value. And so, yeah, this is really implementation details. Because actually when you, I don't think it's the case for registration, but when you perform atlas estimation and you have a high number of images, when you perform one cost to find step on the images, you defilter the images. And so since we are trying to estimate a template image, this means that the defiltering process will tend to make the gradient of the template image be very high because the template image wants to adapt to the new appearance of the images. And if you let the template and the template to subject deformations be modified too fast during gradient descent, this will just tend to block the algorithm into another awful kind of unrealistic local minima. So basically, we need to slow the optimization when we perform the cost to find step. And so we needed especially to make sure that the template image adapted itself before the momentum vectors adapted themselves.
Mm-hmm.
Because if the momentum vectors adapt too fast, this will drive the template image to an unrealistic local minima.
So in practice, how do you do?
In practice, it's just when we reach convergence, we perform our cost to find step. So this means that we will just use a smaller filter on the images. And in what I did, I think that I was freezing the optimization of the momentum vectors during 3 iterations, just to make sure that the template image had time to adapt. I also did, I think I also tried just changing the step sizes and imposing that the step size of the template image was larger than that of the momentum vectors.
Mm-hmm.
So in this dual thing, how do you couple these two different, so you have this momentum kind of multiscale thing, and you have the multiscale on the images or on your mesh. How, I mean, in this they work differently, right? So how do you couple them? How do you find the right levels that they work?
Actually, we also had several different versions. So we had versions where the cost to find steps on the momentum vectors and on the template happened at the same time. We have a version where we iterate, we would perform one cost to find step on the template, then on the momentum vectors, etc. We also had a version where we performed cost to find steps still in this iterative manner, but we could also go back and go. We would go towards 2 fine steps and then go back to the coarser step and then reiterate the process. And the conclusion was that there is no much difference. And to me, the best performing one is the one where we iterate simply between cost to find on the template, then cost to find on the momentum vectors, then cost to find on the template, etc.
But for the cost to find for the template, you have to choose some kind of like kernel size? Like you also apply some kernel and something?
Yes, so we used a Gaussian filter on the images, and since the grid of momentum vectors can be understood in terms of pixel coordinates, we actually can easily know when we are at a given wavelet filter, what is the size of our filter in terms of pixel. And so we just took this pixel size to implement a Gaussian filter on the images, which had an equivalent filter size.
I have a question about the case of the surface mesh. So if I understand correctly, even in this case, the control points are on the grid,
Yes.
enclosing the shape.
Mhm.
And do you think there could be maybe a better way to construct the control points? Because if you want to have a lot of details close to the surface, you need to have a grid with very small pixels. So you have a lot of control points that are in the void in some sense.
Mhm.
And maybe you intuitively more want to have some grid which is close to the surface. I don't know if it's mathematically easy to determine and if you can apply wavelength on this kind of object.
I think we would go far away from our framework, but yes, that's a limitation of the model because it doesn't really make sense to have a grid around a grid of control points around surface meshes. That being said, in practice, deformation is quite efficient on surface meshes. But I think there are many other solutions existing, but I'm not sure that we could modify our grid of control points in this way. We would really leave our mathematical framework, and this would change the problem.
And so for you, it wasn't a limitation. You can achieve the level of detail you want without increasing too much the computational cost. Too much control points.
So this is always a complicated question, and since we have no real ground truth, this is also the question of what really do we want, and in the case of modeling the development of the cortical surface, I actually developed another way of evaluating the trajectories that we were estimating. Which was not based only on distances between our subjects and the trajectory, but also on gyrification indices, which tell us if our brains are folded correctly according to the pregnancy stage. And so when we do this, we manage actually to find a kernel size that gives us the results that we are expecting.
Okay.
But this is really fine tuning, and it really depends on the objects that we are using.
Yes.
And about the geodesic regression, not the geodesic shooting trajectory, you do piecewise geodesic because it's not geodesic concept. Would it be easier to optimize on the trajectory of vector fields instead of assuming a geodesic behavior, or is it not working? Could you try this one?
So I'm not sure about what you're asking. So going from a single trajectory and trying to cut it.
Instead of doing that, just not assuming the geodesic behavior. So estimating at each time a vector field without any assumption on its evolution. Like if you have several time points, you have at each time point you have a vector field, and then you can still integrate.
But if we do not assume is that the vector fields are geodesic, then we are not estimating diffeomorphism anymore.
If it's L2, it's still L2 fine, and they do not expect still a diffeomorphism.
I'm really not sure about this because since we tend to use really small kernel sizes and elevated numbers of control points, I'm not sure, but I think that if we stop assuming that the control points follow geodesic trajectories, we will estimate very irregular vector fields.
Okay.
But you could still regularize the vector fields, right? You can make them like as smooth as necessary in a sense.
No, it's yeah, it would be interesting to try.
Because I know in Varna we use trajectory compression. Laurent Lunet was not for an geodesic person. But I don't know exactly what they use. So yes, instead of putting a golden I don't know.
I know that. Yeah, at CIS, I think they believe that it's better to not to do shooting. And I think also François-Xavier, I discussed with this with François-Xavier a few weeks ago, and so I think there are references, there are articles proving that it might be better to do not to do geodesic shooting.
Isn't the computation much heavier if we don't use geodesic shooting?
No, it takes more memory, but the computation is slightly easier because there's no geodesic equation, so I think it's equivalent.
Yeah, I heard that they are doing they are optimizing the momentum at each time. So then they use the initial momentum to shoot it. So they are sure to perform a geodesic at the final step. And this geodesic is better than if you optimize in the shooting way. You are just it's what we call the sharp
optimization.
Yes, they use it after all those. In fact, they use the shooting and they forgot everything except the initial momentum. And they use this initial momentum to perform a shooting, which is close to the trajectory they had. This one, you are sure that it's a geodesic, so you get a geodesic at the end.
Yeah, but that's when you have only one time point, 2 time point, one start and end.
Yeah.
If you are intermediate, you don't know whether you are.
No, exactly.
Okay.
Yeah.
How do they do
But usually when you do this, you cannot use FBFGS or smarter optimization methods because in what happens is that you cannot make big steps. Actually, your yes. So
it's intuitive.
Related to optimization, you cannot use like Newton or quasi-Newton because you cannot make big steps. So you are bound to just gradient descent with a small step size. So it has to be slow in some way. So it's a bit disappointing.
And why you cannot do big steps?
Because actually your momentum are related to integration. I mean, maybe if you
compute the full range, maybe you can. But if you update at each time step sequentially, I don't know how good
okay, I have to think. I remember I looked at this and my conclusion was what I said, but I don't remember exactly this.
A control code formulation, there are control points also? Evolving following the flow?
Yes.
So maybe that's.
I think. I don't remember actually. Yeah, that's a good question because
we should invite Laurent next.
France.
Laurent, please. Yes.
No, sorry. I'm not sure.
I had some question. Just about your jumping character. Okay, this is highly non-geodesics. That's why it's just completely the fact that the character is going up and then down. Okay, so you can't capture this with the geodesic. That's why the first line of original is completely perfect.
Yeah.
Okay. Why? What is the black magic that makes the multiscale work? Why the multiscale is still kept?
But it's not a geodesic.
No, it does not search.
That's what the red markers stand for.
Oh,
It's piecewise geodesic.
okay. So okay, cheating.
No, no, but even without 520%.
Yeah.
Okay.
Too easy.
Okay. Yeah. So I think we're good.
Yeah.
Thank you.